tell us about some interesting and new results on learning tree structure distributions. Take it away.
Thank you. Yeah, so I'm going to be talking about learning tree structure distributions using an algorithm by Chow-Liu, which is from 1968. So it's been around a long time. People have been using it a lot. It has a Wikipedia page with a lot of citations. And the goal here is to give finite sample guarantees for how accurately, how many samples it takes to reconstruct a good tree. So just as background that probably many of people in the audience understand better than me, we want to learn some high dimensional distribution. Here for this talk, we're going to focus on discrete alphabets. So P is over sigma to the n. Sigma, you can think binary or a small constant. We'll give the dependence on sigma. And of course, learning such a high dimensional distribution is hard because there's sigma to the n different degrees of freedom. It's going to take a lot of samples. And so in order to do this, you need some structural assumption on P. And one way to impose structural assumptions is Bayes nets. So this is where you have some underlying dependency graph, and you suppose that P factors very nicely. So the probability distribution for every variable only depends on the parents in the graph. And so then you can write it down, but if the graph is first, you can write it down very, very nicely. Another way of expressing high dimensional distributions is Markov random fields, which is where you look at the cliques, you get some cost for each clique, you take the product, and then that's the probability for each setting of the variables. And so again, this is something that you can write down. It decomposes just as functions of small pieces of this graph, and so you can write it down efficiently. The Ising model is a special case here, where it's binary. And so these make it easy to write down P, and so you can at least hope to solve the answer. Unfortunately, it's still very hard to learn in general what the distribution is. And so we're going to focus on a very special case, which is when their graph is a tree. And tree graphs are nice for a number of reasons. One being that Markov random fields and Bayes nets are actually equivalent for trees. The exact same set of distributions are expressible for a given tree. And then since MRFs don't have a orientation, that means in fact that the choice of root for your Bayes net doesn't matter either. And so whatever your root is, you root the tree from there, and you can write down a Bayes net for any distribution that's expressible with any other root on the same tree. Okay, and so then if your distribution really is tree-like, then this is great because you can do computation on these tree structure distributions very easily. So for whatever downstream task you have, you can do your computation. And then the hope is that because these are so simple, we should be able to learn them efficiently with a small number. And so in particular, what we would like is we'd like to say, if you can give me any distribution, ideally what we'd be able to say is we can find a tree structure distribution P hat that is at most epsilon worse than the best tree structure distribution. So here I don't know what tree it is. I'm still going to try and learn an approximation to P that's almost as good as the best tree structured approximation. And the way we're going to measure distance is with KL is from P to P hat. Turns out that this is the mathematically cleanest way of doing it. If you want something like TV, then you can use Pinksker's inequality to get bounds into. So any questions on this setup? All right. So for most of the talk, instead of trying to find a good distribution, we're going to look at structure learning, trying to find a T such that the best distribution on that tree T is close to the optimal. And it turns out that finding the tree is the hard part. Once you know the tree, estimating the distribution is not that hard. And so, just as an outline of the talk, we're going to talk about the classic Chow-Liu algorithm for learning trees, and then realize that the analysis of it is going to depend on independence testing in low dimension. And then we're going to solve independence testing in low dimension, and then get back to Chow-Liu and get our good result, and then our linear sample result for the realizable. Okay, so basic background. If I have some tree, suppose I know some tree T, and I want to find what is the best approximation to P that is T structured. Well, the natural solution is to say, well, we'll define our, right? So PT is a product over the marginals because T is structured, and we'll just define PT to match on the marginals with P. So we just look for every probability of B given A, the probability of E given B, the probability of D given B, and take the product of these. And that is tree structured, and we'll just set that. It turns out that that is the distribution that minimizes the KL distance, which is really why we're measuring in that distance, because it makes this very clean. Not only that, but Chow-Liu showed that if you measure that distance to the optimum, you can express it as the negative sum over all pairs of the mutual information along that pair. So in this case, it would be negative mutual information between A and B, between B and E, between B and D, D and F, A and C, plus some function that only depends on the tree and it doesn't depend on T. Some function involving attributes. And so then the point is, this means that the tree that minimizes the KL divergence is going to be exactly the tree that maximizes the sum of mutual informations over this tree. And these are just pairwise functions. So we just want to find the maximum weight spanning tree where we weight every pair by the mutual information of the variables on both sides of the edge. So this is the Chow-Liu observation. And then once you know this, then that gives you a very natural algorithm, which is I just want to define T, I take the maximum weight spanning tree. The only problem is I don't actually know the mutual information between XU and XV because I don't know the distribution on XU and XV exactly. I just have samples. But what is the natural algorithm that you're going to do? Well, you're just going to take the empirical mutual information. You have your empirical, you take a bunch of samples, look at the empirical mutual information, compute the empirical maximum weight spanning tree. And the hope is that the results you get will be optimal or near optimal with a relatively small number of samples. So this is the setup. This is from Chow-Liu in 1968. So there's been a lot of analysis in the past 50 years. And so for a while, this analysis, much of it focused on asking when the answer that you get is equal to the optimal answer. Exactly. So it gets every edge correct. And so Chow and Wagner observed, it's sort of a trivial observation, that as your number of samples goes to infinity, then your error probability is going to go to 0 because you're going to converge to learning these mutual informations exactly, and therefore it's going to give you the correct answer. And then a couple more recent papers have analyzed what the probability of failure is and show that that failure probability goes down exponentially in the number of samples with some constant CP that depends on their distribution. And it's going to depend on the distribution because, well, if I have two edges that are very, very close, then it's going to take a whole lot of samples to be able to distinguish which edge you need. Right? So in this case, I really, Y to Z is slightly better than X to Z. But in order to notice this, I'm going to need to take millions of samples. And so you can't get a sample complexity bound that's independent of the weights of your P. because it's not distinguishable. But of course, in this case, we don't actually need to distinguish edge yz from xz because they're basically the same. And so this gives a natural question is, what if I don't want to find the optimum t star? I just want to find a good enough approximation to t star. And so this now is a question of, can I find at hat such that the KL divergence is in most epsilon more than the optimum KL divergence would be? Does this make sense? So now we can hope to get a bound that depends on n and depends on sigma and depends on epsilon, but doesn't depend on p itself, doesn't depend on the parameters of my distribution. And so Hofgen in '93 actually analyzed basically this. There was a little bit of difference. He didn't do exactly the empirical mutual information. He did a slight variant of empirical mutual information for the weights on each edge, but throwing out some outliers and stuff like that. But basically does that and showed that you can do this with O tilde of n squared over epsilon squared for binary alphabet. Okay, so this is the background. And then what we show is first we get a bound that's similar to Hofgen's for general alphabets. So if you have sigma squared n plus n squared over epsilon squared, then with high probability, Chow-Liu will return a t hat that is epsilon close to optimal. And in fact, as we'll see, this is basically trivial. Like if you just plug in existing results, this is clear. There's not really much to it. However, this is necessary. You can construct distributions such that finding any epsilon approximate t really does require n squared over epsilon squared samples. That's unfortunate because n squared isn't very good. And so our next result is to say, well, if we're actually a tree, right? So the example where it's hard is not very close to being a tree. It's not actually tree structure. And so in that case, maybe you don't really need to learn the distribution as a tree. Like it's not really, you're not trying to solve a problem that's very good to solve. And so our main theorem says, if your distribution actually is tree structured, then we can learn it in n over epsilon samples rather than n squared over epsilon squared samples. And when I say we can learn, I mean Chow-Liu learns it. The straight up Chow-Liu algorithm does it.
Eric, can I ask a question? I'm sort of confused about the realizable case. I mean, if it's a tree, then it's also an Ising model, and we should expect like log in the dimension number of samples to learn it, right?
Oh,
I see. The degree may be unbounded. Okay.
Yeah, the degree can be unbounded, but
still.
So even more than that, like so. I mean, you can have just a bunch of little triangles, and I need to know for each triangle which one it is. Like there's some edge, and then you can have a gap here where it's like my mutual information is epsilon 0 epsilon. So I say epsilon over n. Right? If my mutual informations on each edge can be epsilon over n, then whenever I make a mistake, I'm going to lose epsilon over n and KL.
Yeah. Okay. Your edge strengths could be so small there. I understand how the bound comports with other work. Okay.
Yeah. Exactly. So our knob gives an answer, which is the log n is multiplied by exponential on the coupling strength, and we don't want to assume anything on the coupling strength. And so if that's linear, then your bound is going to be quite bad. So yeah, you actually do need n over epsilon, because in something like this, you can have order n instances, each of which you're off by epsilon over n, unless you take n over epsilon samples to be able to identify what the situation is. And then similarly, we'll get the n squared over epsilon squared by saying that you can make n instances, each of which have a gap of epsilon over n that takes n squared over epsilon squared to learn. Any other questions?
But I guess your point, I guess the point here is that the theorem you don't have any conditions on like the edge strengths.
Exactly. There's no condition on edge strengths, no condition on condition number for any distribution.
I guess the reason why you can get away with that is that you're not doing structure learning here per se. Like you're not identifying the edges of the graph. You're just coming up with some tree that is close.
That's right. So we're not going to get exactly the right tree. Right. And then Costas points out that there is actually an n log n over epsilon bound. So if you, yeah. So in this instance where you know exactly what the triangles are, then it's n over epsilon. But if you don't know exactly how the edges are linked up, how the triangles are linked up, then you can get an n log n over epsilon.
But in this lemma that you're calling trivial, like there's also no condition on the edge strength.
There's no condition there either. Right, so I'm saying it's trivial, but it was not previously published. But it really does follow directly from previous work. Okay.
Quick question: is it clear from your analysis what happens when you have something that's close to being tree structured? Like how you interpolate between these two?
I haven't thought about it that carefully. Yeah, there's a couple places where you need to be careful about how you define being close to tree structured, I think. But it seems plausible to me that you can make it. Yeah, it seems likely to me that you can make it work as long as I'm epsilon close to being tree structured. But I'm not actually sure how it works.
Okay, cool, thanks.
Yeah. Okay, so then of course this is about giving you a bound in KL. If I want something in TV, you can use Pincer's inequality. And so I give you the square root, so then you're gonna get a 1 over epsilon squared instead of 1 over epsilon. But it'll still be linear in it. And then Costas and Daskalakis and Penn concurrently have very similar results. So they also get a linear, a near linear bound in the binary case. So they're in the binary case for TV, but they're actually optimal. So we get n log squared n, they get n log n, which is in fact necessary even for the binary realizable case. Okay, so let's try and prove the trivial lemma. So again, we have that by Chow and Liu, the cost we have is some constant that's independent of the tree minus the weight of the tree and the mutual information. And so for any t, whatever we pick, our KL divergence is going to be opt plus however much worse our weight is. And so the only question is, can we find an approximately large, sufficiently good maximum weight spanning tree? Approximate the maximum weight, get them whose weight is at least epsilon less, no more than epsilon less than the optimum. And so the obvious algorithm is just to do the empirical maximum weight spanning tree, where you weight by the empirical mutual information. And so again, right, so we get this t hat that maximizes the empirical weight, and we want to say that this is epsilon close. So that means we want the weight to be epsilon close. So it suffices to ensure that for every tree, our estimate of its weight is epsilon over 2 close. Because then the optimum we're only going to view as being epsilon over 2 worse. Whatever we output is only epsilon over 2 better. And so if it seems like it's better than the optimum, then it has to be within epsilon. So as long as every tree is estimated to within epsilon over 2, we're going to be good. Okay, well, each tree is a sum of, this is versus the sum of mutual information between x hat and x u and x hat and v. And so in order for this gap to be epsilon over 2, it suffices to have each individual term be within epsilon over 2 divided by the number of terms. And it's a tree, there's only n minus 1 terms. So it suffices to have the individual mutual informations be epsilon over n close for all pairs. And so then that's the question, okay, how many samples do we need for the empirical mutual information to be close to the actual mutual information? With high probability, then we can take a union out and we'll be done. Okay, so this is a question about mutual information estimation. We have some samples from sigma cross sigma, low dimensional, and we just need to know, we want to estimate the mutual information within epsilon. Well, mutual information is a difference of entropies. Suffices to estimate each entropy to within epsilon over 2. People have done this. People have spent a fair amount of time analyzing the plug-in estimator for for entropy, as well as mutual information. And the result of Antos and Kantoyanis shows that you can do this with sigma squared over epsilon plus 1 over epsilon squared times some log factors. Now for Chow-Liu, we wanted to estimate to error epsilon over n. So we plug in epsilon over n, and we need a high probability, so delta is 1 over n. And so you get that n times sigma squared over epsilon plus n squared over epsilon squared times log factors. So with this many samples, every single mutual information will be epsilon over n close. Therefore, every tree will be epsilon over 2 close. Therefore, whatever tree you output is epsilon close to the best tree, which means my KL divergence is epsilon close to the best tree, that of the best tree. So this proves the lemma. Unfortunately, that n squared we have is in fact necessary. You can't beat the n squared for this problem. Why is that? Well, it's so the hard instance. So we're going to take a 4-variable case where we have a central, say in the binary setting, we have some IID W that's 0 or 1, and then Y is equal to W with probably 3/4, Z with 3/4, X with 3/4. All right, so this is some tree. And so then the correlation between the leaves of this tree is going to be 5/8 because it's 3/4 squared plus 1/4 squared is 10/16 is 5/8. Okay. Now, what happens if we vary these weights by epsilon? So if we make these be 3/4 plus epsilon, 3/4 minus epsilon, then what happens is that the X to Z and X to Y weights change by epsilon squared, while the Y to Z weight changes by epsilon. So the Y to Z is significantly less than X to Y and X to Z. Now this doesn't really matter for finding the right tree on W, X, Y, Z, because the right tree is W to, is the W to X, W to Y, W to Z, and these are a constant amount better than the others, and so it only takes a constant number of samples to find this. But what happens? But actually figuring out whether that X is the one with plus epsilon rather than Y rather than Z, well, you need to just identify a biased coin. Am I 1/4, 3/4 plus epsilon over 3/4 minus epsilon? That's going to take 1 over epsilon squared. You don't need to find the tree because you know what the tree is. But consider if I don't have W, I only have X, Y, and Z from this distribution. And I still want to find the best tree on X, Y, and Z. So I've generated X, Y, and Z from this tree on 4 variables, but I only give you the 3 variables. Then the best tree in this case is going to be X to Y and X to Z, not Y to Z, because Y to Z are less correlated by epsilon by the way that I've constructed. But because even if I told you W, identifying that X was the more likely one would take 1 over epsilon squared, then if I tell you just X, Y, and Z, it's going to take you 1 over epsilon squared to identify this best tree. On the other hand, the mutual information between Y and Z really is order epsilon worse than the mutual information between X and Y and X and Z. So I really do need to learn that X is the relevant one to find it. And therefore, in the n equals 3 case, finding the best tree really does take 1 over epsilon squared samples, not 1 over epsilon. And that's n equals 3. If I have general n, what do? Well, I just make a bunch of independent copies of this. And each one of them, I make the gap be epsilon over n. And so then it takes n squared over epsilon squared to get each one with constant probability. So if I have fewer than n squared over epsilon squared samples, then I'm going to get 10% of these estimates wrong. My error, the weight of my spanning tree is going to be off by 10% of n times epsilon over n will be order epsilon. And so in this instance, it really does take n squared over epsilon squared to find the largest tree. So that's unfortunate because we don't want to do n squared. We'd like to do n. But again, this is an example where it's not actually tree structured on x, y, and z. It's tree structured on w, x, y, and z, but we don't have w. And so finding the best tree here isn't actually a very good thing because it's not actually very close to tree structure. And if you try to construct such an example with a actual tree, you find that it's hard. That you can't make it, yeah, you'll find that you run into difficulties, and this is why. So if x, y, and z are actually tree structured, so say if it really is generated x to y, y to z, then we're going to show that you can do it in order O tilde of 1 over epsilon, 1 over epsilon log 1 over epsilon samples, rather than 1 over epsilon squared. And the point is, we don't need to estimate every mutual information up to order epsilon. That's hard. Learning the mutual information is hard. But we don't need that. All we need to know is the relative order of the mutual information. So we need to know if the mutual information between y and z is bigger than between x and z, then we should find s. Which means, equivalently, we need to be able to estimate the difference of mutual informations. And so what happens is, if the mutual information between y and z is very close to that between x and z, then x and y have to be very, very correlated. And so your estimate of the mutual information between y and z and between x and z are very, very correlated. And so your errors are going to cancel when you subtract. That's a bit of intuition. The key observation mathematically is that if I take this difference, mutual information between y and z minus between x and z, this is equal to the mutual information between y and z conditional on x minus the mutual information between x and z conditional on y. How do you prove this? Well, you just rearrange terms. So if I take the mutual information between y and z plus y and z conditional on x, this is equal to mutual information between y, x, and z. Because there's this conditional, the chain rule of mutual information. Similarly, if I take x, and this one. If I take the mutual information between x and z plus mutual information between y and z conditional on x, again, I get mutual information between y and x conditional on z. And so this, again, is just a rearrangement of the chain rule of mutual information. And then the observation is, well, in order for it to be bad, in order to actually care if I mistake yz for xz, this left difference has to be at least epsilon. On the other hand, because I'm actually a tree, and this is where we use that it's realizable, the mutual information between x and z conditional on y needs to be 0. That's what graphical models give you. X and z are independent, conditioned on y. And so that means then that the mutual information between y and z conditional on x better be at least epsilon. And so now, if I want to know is this difference greater than or equal to 0, it's now a question of testing rather than learning. Because the same equality happens for the empirical mutual informations. And so the mutual information between x and z given y is 0. And so the empirical mutual information, if I just want to test are x and z independent condition on y, will be less than epsilon over 10 with a small number sample. And y and z condition on x are not independent. And so I just need to test that, and I'll get that my empirical mutual information is more than a constant times epsilon. So then when I subtract, I'll get something bigger than 0, and therefore the empirical estimate will choose yz over xz and won't make a mistake. So we're saying that as long as we can test, we can distinguish when the conditional mutual information is 0 from when it's bigger than epsilon, then we're not going to make any mistakes that are important. And so we're going to be able to learn the n equals 3 case in O tilde of 1 over epsilon samples as long as we can test in O tilde of 1 over epsilon samples. So estimating the mutual information itself is hard, but just testing if the mutual information is 0 or big is not so hard. Saves you a quadratic factor. And so that's why we're now talking about independence. So here the basic question is, how many samples do I need to distinguish my mutual information being equal to 0, as it is on the right, from being bigger than epsilon, as it is on the left? And it's a little complicated, so let's start with a simpler version of just independence testing, not conditional independence testing. If I just get pairs over a finite alphabet, I want to distinguish are x and y independent or not? Are they far from independent in mutual information? And then for the actual Chow-Liu algorithm, we need that the test statistic that we use is the empirical statistic. I think it's an interesting question whether you could avoid that and apply a general statistic. But because we use this identity for the test statistic as well, it's actually very helpful for us that our test statistic is the empirical mutual information, so that it satisfies this identity as well. So mutual information testing is something that people have studied in property testing for a while, but mostly they've been focused on testing with distance measured in total variation. So distinguishing distinguishing independent from far from independent by epsilon in total variation. And so there have been works by Diaconicus and Kane, as well as something I did, that try and really nail down the dependence on the alphabet size and on epsilon and on failure probability for this problem. And then Canon, Diaconicus, Kane, and Stewart extended this to conditional independence testing and also got exactly the right dependence as a function of the alphabet size when you're measuring it in distance in total variation. And then they applied this for measuring distance in mutual information, as we actually care about, but they get a 1 over epsilon squared bound because they're just applying their total variation tester to KL. And so they observed that this is like their hard instances don't seem to require this. And so it seemed likely to them that you could do better, which in fact we're going to do. And so our goal is now to get a 1 over epsilon bound with some dependence on sigma, which may not be optimal, but we'll be polynomial. And so this is our theorem. It says that as long as n over log n is bigger than sigma squared over epsilon, then with high probability, the empirical mutual information is within a constant factor plus or minus epsilon of the actual mutual information. So this is an approximation, but it's sort of pretty weak. It's saying we can lose a constant factor and we could lose epsilon, or we could gain a constant factor and gain epsilon. But the consequence of this is that we can distinguish mutual information being 0 from being bigger than epsilon. Because if we're 0, our estimate will be less than epsilon over 10. If we're bigger than epsilon, our estimate will also be bigger than epsilon over 10. And so then that's all we need for Chow-Liu. And then we're going to extend this to conditional mutual information, which is actually what we need, but it's losing another factor of sigma. Now, these dependencies on sigma are probably wrong, even for mutual information, even for the empirical statistic, let alone arbitrary statistics. But these are the right epsilon dependence. You can't do any better than that. Which, for application where we really care about epsilon because epsilon over n is what matters. Okay, so let's describe some simple examples. So in the symmetric case, suppose I have that x is equal to y with probability p. So my mutual information being 0 would be saying that p is a half. So if I want to estimate p, right? So if my mutual information is more than epsilon, because entropy is a quadratic, I only need to estimate p up to error square root epsilon. So if x equals y with probability a half plus square root epsilon, it's still the case that their mutual information is only epsilon. And so sure, estimating it up to that, you lose a quadratic factor, but you gain a quadratic factor from the entropy having derivative of 0 here. And so in this case, yeah, it only takes 1 over epsilon samples to estimate p up to square root epsilon, which gives you epsilon in mutual information. Another trivial case is suppose that x is always equal to y, but its probability of being non-zero is p. Well, now my mutual information is just the entropy of p. And so my information is 0 if and only if p is 0 or 1. And if it's bigger than epsilon, then p has to be bounded away from 0 or 1 by at least epsilon over log 1. So now this is the question of distinguishing a coin with probability 0 from a coin with probability epsilon over log over epsilon. Well, you flip it 1 over that many times, and you're probably going to see a heads if it is non-zero. And so you're going to be able to do this distinction. And then the general case, let's let py be the probability that x is 1 conditioned on a given value of y. And so my mutual information is the entropy of h of x, which is the entropy of the expectation of py, minus the expectation of the entropy of y. And so what's going on here is I have py being taking one of two values, and my mutual information is this gap between the entropy at the expectation and the expectation of the entropy. And the point is, well, the linear terms here cancel. And your error, if you Taylor expand around this average, your error depends quadratically on p1 minus p0. And so, okay, there's some log factor from the h double prime, but this means you only need to estimate p up to square root epsilon, which again only takes 1 over epsilon samples. So this is for the binary case. In general, what we do is we say, you take their mutual information, which is a KL divergence, and you can express it in terms of delta xy, which is how different it is from being independent. And you can subtract off the linear term, because the linear terms all sum to 0. Because the sum of pxy is 1, the sum of pxpy is 1. And when you do this, you get that your mutual information is a sum of terms, each of which is positive, and when they're near 0, is quadratic, not linear. And so then it suffices to estimate every one of these individual terms well, up to constant factors, plus or minus epsilon. And so if I want to estimate each of these individual terms well, okay, you do some turn-off analysis and you can get this done, which I'm going to skip because just basic turn-off bound, a little bit of analysis. And so that gives you independence testing, which is in the unconditional case. If I want conditional independence testing, well, there must exist some value of z that are far from independent. And so I just need I need a number of samples from that z. And so you lose a factor of sigma to get enough samples for the particular z that makes it non-independent. And so then you can get the conditional independence testing. All right. So back to how we apply this. So for the n equals 3 case, remember, we're trying to say if it's important to pick yz over xz, then the difference must be bigger than epsilon, which means that, well, x to z given y is 0, the other must be at least epsilon. And so our empirical tester, because it gets a constant factor plus or minus epsilon, is going to have the second term be less than epsilon over 10, the first term be bigger than epsilon over 10. And so the difference is bigger than 0, and so we're not going to make a mistake. Great. What happens in general? Well, suppose we make a mistake and pick some edge wz that's not in the true tree. Then we can walk in the true tree from w to z. And because we have a spanning tree, there's some edges between w and z that are in the true tree that we didn't pick. Turns out, simple deduction says you can pair them up. You can pair your edge to an edge that you didn't pick that you should have picked in a way such that each edge you didn't pick gets paired to a unique one that you did pick on this path. And the claim is that difference, if I made the mistake, that difference can't be very big. And so it can't matter much. Suppose it's not true. Well, then the mutual differential between x and y minus mutual differential wz has to be, by definition, at least epsilon over n. And now we want to do the same trick we did for n equals 3. So we do this by introducing the information between z and y, subtract it and add it. And now the left term and the right term are both differences with only 3 variables. And so we can apply the same n equals 3 case, and we get that a difference of conditional mutual informations and a difference of conditional mutual informations. And you look at the negative terms, both of these are 0, because x and z condition on y is 0, w and z condition on y is also 0. And then because I'm bigger than epsilon over n, one of the positive terms must be at least half that. And so when I look at the empirical values, well, with n over epsilon samples, or tilde of n over epsilon samples, my empirical values for the ones that are independent will be less than epsilon over 10n. And for whichever one is large, will be more than epsilon over 4n. And so then, and the other one, I don't know, but it's non-negative because it's mutual information. And so when I add that, I'll get something positive, and that says I would not have made this mistake. So I will never make a mistake by more than epsilon over n. And so that means that the total number, the sum over all mistakes I make is less than epsilon, which means I find the good tree. Now the question is, okay, this is for structured learning. What if I want to actually learn the distribution? So that means I need to estimate PT. The natural suggestion is to do the empirical estimate. This doesn't quite work because KL divergence is very sensitive to having zeros. So if my empirical estimate is 0 somewhere, because I just never see a rare value, then I'll get an infinite KL divergence. The standard answer for this is, well, I shouldn't be totally surprised by something I didn't see. Let me use Laplace's rule of succession. So I just do an add one estimate. Suppose at every alternative I get one more of them. And then you can say that this works. And to prove this, we just need to say that the add one estimate converges, is very accurate in KL. This was proven in previous work in expectation, but we actually needed a high probability so we can union bound over all the vertices. But it's actually quite straightforward. In fact, it used the same decomposition that we had where we subtracted off the linear terms and get something in terms of a quadratic and a x log x. So it's actually really the same technology to get conversion that the Edwin estimator is accurate with high probability in KL. And that's basically it. So we get n squared or epsilon squared samples suffice in general, but when you're actually tree structured, then you can do an n over epsilon. So a number of obvious questions. So one would be to get optimal log factors. So as I said, Daskalakis and Pan can get this for binary alphabets. What if we have a general alphabets? Another is the dependence on our alphabet size is presumably wrong. And this is true even for conditional independence testing. So if you could improve the conditional independence tester, that would immediately give you a better bound for Chow-Liu. And then, okay, you can look at continuous distributions like Gaussian graphical models, and you can look at bounded tree width, would be a natural extension of trees. So thank you.
Cool, thanks, Eric. It's really interesting. Do people have questions?
Yeah, I have a question. So among these obvious questions that you mentioned, like, is there, would it just be like would it be some sort of extension, like repeating this game, or are there new ideas, for example, needed to deal with continuous distributions, right? So what are some like obvious roadblocks from like generalizing this result?
Yes, well, so continuous distributions, I don't actually know very well. I think, Costa sent me an email yesterday saying that he thinks they know how to do continuous distributions. But I haven't thought about that at all. For better dependence on sigma, the roadblock is our exact theorem statement is not true with a smaller sigma. So we say that the mutual information between x hat and y hat is theta of mutual information between x and y minus epsilon, plus or minus epsilon. And that's not true with less than sigma squared samples and sigma cubed when you do with the conditional version. But we don't actually need that. So what will happen when you have fewer samples than that is that the mutual information is going to seem bigger than it actually is, because there'll be some spurious correlations because you don't have very many samples. But if you're non-independent, it'll probably seem even bigger than it actually is than if you are independent. And so the same thing happens in uniformity testing, which is really a special case of independence testing when it's uniform. So I want to test that something is uniform, then the empirical tester works well below the regime where it's accurate in estimation, because it's still, there's still a bias to be smaller if I am independent, if I am uniform than if I'm not. And so here you should expect a bias to be smaller if I am independent. Bounded tree width, I also haven't thought that very carefully. You can get something exponential in the tree width, so your algorithm is not as clean. But seems likely that should just be doable.
Okay, thank you.
Eric, I have a quick question. So I guess you've thought about using some of these more sophisticated entropy estimators to estimate your mutual information instead of the plugin?
So the problem is estimating mutual information really does take 1 over epsilon squared. Because if you think about, like,
you could gain in a log factor somewhere.
What is it?
You could potentially gain in a log factor somewhere.
Oh yeah.
I'm wondering if that's the extra log factor that you have.
Right. So I mean, yeah. So I mean, we're using union bounds all over the place, and so when you have a extra log factor, then it becomes very, very nice that you can just use union bounds and not worry about averaging things.
So think like if you go through KL to bound TV, you have to lose a log at least in 1 over epsilon, because like you gave an example, Eric, where I think you gave it, like where the mutual information is epsilon over log 1 over epsilon, but the TV is epsilon, like, or the other way around, right? So you
The
can.
TV is epsilon over log 1 over epsilon. The mutual information is epsilon.
Yeah. So if you go through like KL, you have to lose this factor, right?
Yeah. Right. And so then like your epsilon, when I do these independent copies, I get n, I have n versions of this. So my epsilon is epsilon over n. So you sort of lose a log n over epsilon. It's not. Yeah. I'm not sure that you need to lose for the final problem, but
you lose a log 1 over epsilon. I have to think about whether you lose also the log n.
right, because your effective n is epsilon over n when you do these n copies, which is, but then it's not clear that but then there's also a log n that you lose from learning the structure. So it's not clear if you need both at the same time, but it seems plausible you would.
Cool, thanks. Yeah.
Eric, is there like a quote unquote trivial lemma for like the bounded tree width case, or does that become non-trivial?
So yeah, I guess it's not totally clear what the algorithm is for the bounded tree width case, because they're not, I guess you've got to be looking for a maximum bounded tree width graph on mutual information. Yeah. So yeah, it's not, it seems likely that people have studied this, but I don't know what the algorithms, what even the algorithms people have done are.
Okay.
Perfect. Well, thanks, Eric. The next speaker is Antonio Blanca, and he'll talk in 8 minutes. So there's a little bit of a break. Feel free to go get some more coffee, and he'll tell us about hardness of identity testing for some families of graphical models. So see everybody in a